Okay, this video that we're looking at here is going to be the first video dealing with the functional group of ethers, epoxides, and sulfides. And what we're going to look at in this video is predominantly their physical properties and the synthesis of simple ethers. We'll get to epoxides at the end of this chapter. Okay, all right, so ethers are basically analogs of water where both of the hydrogens of water have been replaced by alkyl groups. If we look at the structure of an ether, like you see here, okay, we see that it has these strong dipole moments that you would associate with a carbon-oxygen bond and its polarity. Okay, we also have lone pairs of electrons at oxygen, which can function as hydrogen bond acceptors. Okay, all right, so ethers can engage in this type of hydrogen bonding, the oxygen lone pair, and water, if you have a different hydrogen bond donor molecule added. But a ether that's 100% pure will not have any hydrogen bonding. Okay? What we find here is that the boiling points of ethers very much resemble those of hydrocarbons. The dipole-dipole attractions don't really add that much to the degree of intermolecular attractions. The boiling point of pentane is very much similar to the boiling point of diethyl ether, even though they both have relatively similar molecular weights. However, if we take this compound in butyl alcohol, we see that the boiling point is much higher at 118 degrees, and this is due to the fact that it has hydrogen bonding. Okay, now, even though this isn't really adding much to the boiling point, it's having a major effect on the water solubility. Pentane is completely insoluble in water. However, ether, you can dissolve as much as 69 grams of ether in a liter of water. Okay, so ether has a much higher water solubility, and that is due to this ability to engage in hydrogen bonding with water, as you see in this picture over to the in the middle here, middle right. Okay, and what we're seeing here is that when we compare the water solubilities of ether and n-butyl alcohol, they're not really that different. Okay, and as a general rule, ethers will have an appreciable water solubility if there are 6 or fewer carbons per oxygen in the molecule. All right, so ether is commonly used as an extraction solvent. Okay, so how do we do that if it's so water soluble? Well, it's not that water soluble. If we have ether water mix and it exceeds 69 grams per liter, we have ether water saturated with ether on the bottom, and ether saturated with water on the top layer. Okay, so extractive methods are commonly used in organic chemistry, and I'll tell you the first time I ever did an extraction, I smelled the layers, and that doesn't work because they both smell like ether. Okay, and that's because of this effect right here. All right, let's look at a special type of ether, and this is the crown ethers. They won the Nobel Prize for Chemistry, I think like 1995, something like that. Okay, so if we take this compound, 18 crown 6 right here, that's what it's called, and It has a very high affinity for potassium. Okay, so if we have potassium fluoride, it's mostly an ionic compound, but it's not completely an ionic compound. It'll form a very strong complex between the oxygen lone pairs and the potassium empty orbitals. Okay, and what we're having here is a complex to potassium, but this leaves fluoride all alone. And this fluoride here is 100% ionic. It has no bonding interaction with the potassium. Okay? All right, so what effect does that have? How does it benefit you? Okay, so let's imagine that we're using fluoride as a nucleophile in an SN2 reaction, like here. All right, fluoride's not the world's greatest nucleophile, but it can be used in that way. So we take a primary tosylate, potassium fluoride, an SN2 reaction, and we find that this reaction requires kind of a long time to go, and it's not really all that efficient. It's hard to make it go to completion, but if you add a little bit of 18 crown 6 to this reaction goes much faster and proceeds in a lot higher yield. This is because our fluoride is purely ionic. It's purely F-. There's no covalent Kf character left when you have 18 crown 6. Okay? Shorter ethers like 15 crown 5 are more selective for lithium, and so crown ethers are commonly used to extract metal ions because of their high affinity to various metals, and the fact that you can easily control their size by just varying the amount of CH2 groups in the structure, like you see here. Okay, all right, here's a problem. Again, like in all these problems here, you should do them yourself and then pause it, then restart it, and see the answers. Which of these compounds will have the greatest water solubility? Okay, the predominant thing we're looking for is the ratio of carbons to oxygens. Okay, we're not looking for the boiling point, we're looking for the water solubility here. All right, so the first one has a 7-to-1 carbon to oxygen ratio. The middle second one a 3-to-1, third one a 3-to-1, and the last one has basically a 1-to-1, 3 carbons and 3 oxygens. And this is the one in the far right that we should choose as the most water soluble. For water solubility, it doesn't matter whether it's an alcohol or an ether. That's kind of a minor effect. Their water solubilities are quite similar. So this last one is the most water soluble of these compounds. Okay, which of the reactions below will be most accelerated by the addition of 18 crown 6? All right, so what we're looking for is a reaction where a covalent bond character to potassium might be slowing down the reaction. And this is the only reaction right here where that's the case, okay? There are 2 reactions that technically have potassium in them. Why isn't that one accelerated? Okay, well, it turns out that this is the Diels-Alder reaction, and there's the mechanism. We just do the bond reorganization like that, and the oxygen-potassium bond is not really involved in the reaction. It has a little bit of an effect on the electron richness of the dienophile part here, but it's major, but that's kind of a minor. Actually, crown ether would hurt this reaction because it would make it more anionic, and that's not good for the Diels-Alder reaction. So 18 crown 6 is selective for complexation to potassium. If we had a purely ionic compound, this would be more reactive. There was no potassium-oxygen covalent character. Okay, let's look at how we make ethers. Earlier, when we studied the SN2 reaction in Chapter 8, we saw what is actually in this chapter is also the major reaction for making ethers, is to take an alkoxide, and remember we can represent it this way, or we could represent it this way, but we're smart people. We know that the oxygen-sodium bond is predominantly ionic, so these are two representations of the same thing. Okay, and this will just do the SN2 reaction to produce our product. Okay, some other reactions that are worth noting here. I don't think they're in the book, but I'll just say something about them. Okay, if we take some of the alcohol forming reactions from the double bond chapter and replace the water with alcohols, you actually get ether. So remember that we could do this halohydrin formation by adding bromine and water, and this will be an anti-addition. Well, all you have to do is swap out the water with methanol, and you get an ether instead of an alcohol. Okay? Oxymercuration, shown here in red, if you just replace the water with an ether, same general process will occur, and you'll end up with, instead of getting an alcohol, you'll get an ether as the final product. The other process we've had that makes ethers is nucleophilic aromatic substitution. Okay, so if we have a really good electron withdrawing group, ortho-para to a halogen, and fluorine is the best halogen to have here, and we treat it with an alkoxide, we will get substitution at the aromatic ring. Remember that this is not the SN2, so it doesn't violate the old principle that you can't do SN2 reactions at sp2 carbon. Okay, that's a mechanistically more complex process that we covered a few weeks, or at the end of the first half of the class. Okay, all right. Let's look at this reaction, and we're now going to give it a name. We're going to call it the Williamson ether synthesis. Okay, I don't think back in the SN2 chapter we gave it a name. Okay, all right, so here's how we conduct the Williamson ether synthesis. We're going to take an alcohol, and we need to pull the proton off. Remember, the pKa is 16 to 19. This is going to make our alkoxide, and we're going to add the alkyl halide. This is going to do the SN2 reaction, and we're going to get our unsymmetrical ether. This is usually done in one operation where somebody adds the base, waits a few minutes, then adds the halide. Okay? All right, the trick here, or the catch here, is that the most common base that we've probably used in the past, sodium hydroxide, it's not strong enough to do this reaction. Okay? The pK of water is about 16, so if you use sodium hydroxide, this reaction here at the top with base is just going to be in equilibrium, and you'll have to worry about sodium hydroxide being a nucleophile as well as your alkoxide. All right, so we have to use bases that are much stronger than KOH, or sodium hydroxide. These are the bases that we're going to use commonly. Sodium hydride, potassium hydride, sodium metal. This is not actually a deprotonation. This is a reduction. And silver oxide. This has the advantage that the halide precipitates as a silver halide when you use the silver salt. Okay, all right, so when we do the reaction here, first step, KH is going to give us this, and hydrogen gas as our byproduct, and we're going to add the halide, and this gives us the ether. This has all the same limitations of the SN2 that we've come to know. Just remember for the SN2 that methyl greater than primary, greater than secondary, greater than tertiary, and SN2 competes with E2. Okay, all right, so here's another example of the SN2. Here we don't have a deprotonation step, but it's the same general idea, and we get the ether as the product. Okay, so here is a problem for you. Okay, I sort of have a little problem with the animation because I have the answer sitting there for the bottom one. Sorry about that. Which synthesis of ethyl sec butyl ether is better? We'll call these synthesis A and synthesis B. Okay. All right. So as far as like which of these two is better, all you need to know is that this is primary, this is secondary, and we're really looking at which is the better SN2 reaction. We just looked at the trends in the SN2 reaction in the previous slide, and the primary halide is much better. All right, so the SN2 at secondary carbon and a strong base is going to give us mostly the E2 reaction. We're going to get not this. We're probably going to get the alkene as our major product. And this SN2 reaction at primary carbon is going to be successful. Okay, this other reaction won't work. Why? And we're going to design an alternate synthesis. Okay, already got the answer sitting there. But it doesn't work because we can't do SN2 reactions at sp2 halides. Okay, so this is not an SN2 substrate. Okay, so the way to do this is just to reverse the position of the oxygen and the halogen. And if we had the oxygen here, just use phenol here, base and ethyl bromide, we should get this product here quite efficiently. Okay, we'll see that later in this class that phenols are more acidic types of alcohols, and our options for bases are much better here, but the general idea here is that you want your SN2 substrate to be something you can use in the SN2 reaction. All right, so we can also do this with sulfur analogs. So a thiol, like here, is a little more acidic than an alcohol. The pK is about 11, so we can use sodium hydroxide or an alkoxide to do the deprotonation step here. Now we've got a thiolate as a nucleophile, and these are actually more nucleophilic and less basic compared to OR-. So SN2s are much better than the SN2 alkoxides. Okay, so we get a faster SN2 reaction and less competition from E2 reactions. So even secondary halides almost always work when we have thiolate nucleophiles. So in this bottom equation, we have the this is reacting with sodium hydroxide, and then we're treating it with a secondary and benzylic halide, and that's giving us the product that you see there. Okay, let me just say one other nomenclature point. We don't call this a thioether, we call this a sulfide. Okay. All right, so this is the end of this video. The next one we're going to talk about reactions of ethers.